through, they can come in halfway through the introductions. Does that really matter? All right, good morning everyone. We've got a lot to get through this morning, so we're going to start on time with the hope of finishing on time. I'd like to begin this morning's tutorial by doing an acknowledgement of country. I'd like to begin this tutorial by acknowledging the traditional owners on the land on which we meet today, paying my respects to elders past, present and emerging, and extend that respect to Aboriginal and Torres Strait Islander peoples here today. I hope you're all here to discuss enabling teleprotection over packet switch networks, and if not, you might be in the wrong room. On a side note, on this slide is an overview of the topics we'll cover this morning, and included in this will be 2 case studies. We have quite a lot to cover, so I'll ask that you hold all but the most burning questions to the end. Am I doing? Oh, I've got the wrong slide looking. Sorry, apologies. Right, sorry. That is what we'll be talking about today. My name is Brenton Ardenberg. I'm the Principal Engineer Digital Technology at Electronet. I specialise in packet switch networks and cyber security, and I'm leading Electronet's transition to from a combined TDM and IP network to a unified packet switch network.
Hi everyone, my name is Santos Gorella. I'm a telecommunications engineer at SA Power Networks. So I've done my master's degree in telecommunications engineering with bachelor's in electronics and communications. So I've been working with SA Power Networks for the last 11 years. Starting as a graduate. Going through it with the MPLS rollout that the SA Power Networks has been doing, I've been actively involved in the last 5 years with the design and rollout of MPLS network in the metro areas, and then the transition of the TDM-based services to the MPLS network.
And I'm James Cole. I'm the Zone Substations and Secondary Systems Manager at Evo Energy in Canberra, Australia. I've mainly got an information technology and communications background, but I've also got some training and engineering as well under my belt, and also a Master of Business. So, look, I'm currently leading a big technology upgrade for Evo Energy. One of the big parts of that, of course, was rolling out a new communications network to support our operational systems and teleprotection. So a bit about Evo Energy. So I guess everyone's heard a lot about Queensland, how big Queensland is. Evo Energy, we're from the ACT, which is the smallest territory in Australia. Essentially, we're a one city state or territory, if you like. We've got a very important network, don't get me wrong, but quite a small network. So we've got 208 kilometres of 132 kV transmission. We run 16 132 kV to 11 kV distribution substations and, or zone substations, I should say, and about 4,700 distribution substations and 5,000 kilometres or thereabouts of distribution. So a bit about our teleprotection journey. So we embarked on this technology upgrade in 2014. We started by, I guess realising that lookout protection clearance times weren't up to scratch, so we needed to provide communications enabled and accelerated protection systems across the transmission network. So we started by rolling out optical fibre. Obviously, optical fibre is a large investment. We couldn't roll out the fibre quick enough across our entire network to meet the requirements of the protection. So we also augmented that with some leased fibre and also some underground fibre that we already had. On top of that, we've implemented a MPLS IP network to all the zone substations. And I guess that comes with two challenges. One was, like I said, just rolling out the optical fibre network took too long, so we needed to get this thing up and running pretty quickly to meet those protection fault clearance times. And the second challenge was, like I said, not having enough dark fibre for teleprotection. So that's where, having the MPLS network, we needed to find a solution to put the teleprotection using C3794 over the IP network.
Thanks, James. Electronet own and operate South Australia's transmission network. The network includes voltages from 66 kV through to 275, and we're soon to add 330 kV to the mix. To operate the transmission network, Electronet operate a telecommunications overlay network that includes roughly 50 standalone telco sites. Our electrical network consists of 100 substation sites and 600 kilometres of transmission lines. 10 years ago, Electronet started its journey to a unified packet switch network. This included the convergence of several standalone IP networks and the conversion of several serial-based services over to a packet solution. The journey included the transition to packets for all operational network traffic, including long-term support for teleprotection and SCADA, which has been central to the design of our packet switch network.
Thanks, Brendan. Okay, as explained on the slide itself, SA Power Networks is a sole electricity distributor for South Australia. So what we do is we take 66 kilovolts from Electronet, which is our transmission company there, and then we work from anywhere from 66 right up to the low voltage to the customer premises. And then from there, the retailers take over. So going to the next slide, what we do have at the moment is 51% of SA Power Networks is basically owned by Cheung Kong Group, and the rest 41% is by a Canadian and US-based investment fund. We do have an extensive network throughout the South Australia, and then if you have a look at it, we cover around 850,000 customers. And that's the data from last year, so it may be even more. Okay, moving on to this one. This slide actually gives you over the evolution of MPLS network for SA Power Networks as a whole. It started from 2012, 2013 when we started looking for a replacement for our old TDM network. And then since then, from 2012 till 2023 now, we basically have got around 100 substations which are on MPLS network, around 150 teleprotection, a bit more than 150 teleprotection services that are already on MPLS, and around 40 substations which are purely MPLS, which we have taken out the SDH and PDH altogether. now. And last year, in November, we actually did the first commissioning of our Goose teleprotection intertripping scheme for the CBD pilot, which I'll talk about a bit later with how we did the lab test and stuff. Now, this slide gives you a brief overview of how we stand in terms of teleprotection scheme. We do have 150, as I said on the previous slide, we do have around 150 teleprotection services on MPLS network now. And most of them are C3794 with few exception of mirrored bits and G703 circuits. All teleprotection services are based on fiber links. We haven't done anything because we do have an extensive range of fiber network around the state. So all our teleprotection services between the metros are between fiber links. So with the teleprotection, what we have been doing is they are all SDP based with RSVP traffic engineering, which with path defined hop by hops. And what we have been doing is we have been, for set 1 and set 2 protection, we have been providing a primary path and a standby path. So the set 2 primary path actually becomes a standby path for set 1. And the set 1 primary path becomes a standby path for set 2. And in that way, like if there is a failure or anything in the network, we don't see any failure in the system. And one more thing is what we have done is all our areas have been grouped into different areas as part of OSPF. Every other systems like the SCADA or telephony, everything has to go past area 0, but with the teleprotection, most of our teleprotection services sit within the same area, with some of them actually transversing between areas, and with those ones, we have allowed it to go from one area to the next area without transversing through area 0. Okay, now I will hand over to James to go through the teleprotection.
Thanks, Santosh. Yeah, look, before we get started with the actual technical details of the communication side, it's important to understand, our protection scheme, applications, and a bit about protection. So I'll just give a very high-level summary of the most common teleprotection methods firstly, and then we'll get into some protection scheme basics. I guess just before I get started on this, I guess the important thing is when you're implementing teleprotection, it involves two disciplines. It involves the telecommunications and also the protection disciplines. It's very important to build that trust between the two parties and understand each other's concerns and how the systems actually work. If you're a communications engineer, understanding how protection works, and likewise for protection systems. So traditionally, teleprotection, first off started off using the old copper pilot wire systems, which was direct copper connections between relays. Likewise, the modern day equivalent's optical fibre, which is direct connection between relays once again, generally using proprietary protocols between relays. We've also got some older serial protocols that are used, typically over power line carrier or over radio or optical fibre systems. And then TDM networks, so PDH, SDH over optical fibre, microwave, leased line, and typically this uses C3794 or E1s to the actual protection equipment. And then topic for today really is the emergence of using IP packet networks for teleprotection. So a bit about some, protection schemes that use communications enablement. So we've got trip transfer schemes. So typically these are like low time criticality, up to 10 milliseconds of latency is okay. We just need to guarantee that the trips are going to arrive at the remote end within a reasonable time frame to meet the protection fault clearance times. And types of schemes there are basic inter-tripping schemes, direct transfer trip, or circuit breaker failure, trip transfers to the remote end of a line. So, like I said, you know, low time criticality, not particularly latency intensive. If the trip does get delayed, it really results in non-tripping of the line, which protection perspective isn't great. You know, we want to make sure the line's protected, but there is backup protection, obviously. Important thing is it's kind of fail-safe, so any issues with the communications, you're not going to start tripping your transmission network. Then we've got trip acceleration schemes. Once again, low time criticality, 10 milliseconds of latency still okay. Some examples are some of the permissive overreach trip transfer schemes like POT schemes and then PUT schemes. Once again, look, if that trip acceleration signal doesn't reach the remote end, all you're really going to do is delay the tripping of the line. So not great from a protection perspective, but at least you're not tripping off the transmission network again. So the next scheme is a trip blocking scheme. This has got medium time criticality. This involves sending like a blocking signal from one station to another station to block the protection operation, so you don't get coincident tripping of non-faulted parts of your network. It's got medium time criticality. Just need to make sure that that blocking signal gets the remote end in time to block, to not trip the other section of the network. And problem is though, if that signal gets delayed or it doesn't arrive at the other end, you're going to start tripping off the other part of your network. And the last type of protection scheme is analog schemes. So this is high time criticality. You certainly still want less than 10 milliseconds of latency. That's okay. What's really critical with these systems is the actual range of deviation in your communications latency, your jitter and your path symmetry, or you can't tolerate asymmetrical communications between the forward path and the reverse path. And typically that's a line current differential scheme, which is really the focus of what we're talking about today. We will also touch on some trip transfer schemes with the Goose scheme that Santosh is going to talk about later. So once again, delayed comms or varied comms can cause the line to trip, so high criticality there. So I'll just go through a bit of a high-level example of a couple of these schemes. So first of all, distance protection, okay? So the way distance protection works, you have a zone 1 and a zone 2 and also a zone 3, but zone 1 reach typically protects the first 2/3 of a transmission line, and your zone 2 reach protects the entire transmission line plus into the adjoining segments. So to make the protection coordination work, typically zone 1 will be on instantaneous tripping to trip for the fastest time on that line you're trying to protect, but then you've got to delay the zone 2 tripping to allow the protection on the adjacent circuits to trip in time and not trip. So from a protection perspective, we'd really like to trip instantaneously or as quickly as possible on the actual transmission line itself. So that's where accelerated distance protection schemes come into play. So this is an example of a POT scheme, an overreach trip transfer scheme. So the idea here is that we send the zone 2 protection pickup from the, well, in this example, from say substation 1 to substation 2. And at substation 2, we've got some logic there to say that if you get a local zone 2 pickup and you get a remote zone 2 pickup, put it through a AND gate, then you can trip the circuit breaker instantaneously knowing that the fault is actually on the transmission line you're trying to protect. So as a backup also, you've still got a delayed zone 2 pickup, so if the protection was to fail, like I said earlier, you'd simply delay the protection operation, but obviously that's great from a protection perspective with the communications because you're tripping instantaneously for faults in that transmission circuit. So this is just a summary of what I've spoken about already. So the permissive zone 2 operation must be detected at the remote end for the accelerated trip to operate. The accelerated trip will only occur for the protected transmission line you're trying to protect, so that's a secure tripping scheme. The failure of the communication channels will disable the accelerated tripping, so that's good. It's a fail-safe from a protection and communications perspective. And the exchange of the permissive signal is non-time critical. So generally 10 milliseconds latency is still okay. We'll simply just delay the actual tripping of the operation of the scheme itself by that latency figure. So the other example I'd like to present is the line current differential scheme. So this scheme sends analogue signals from the local end of the transmission line to the remote end via a telecommunication channel. Importantly, the way this scheme works, it's basically sending current waveforms or current vectors from one end to the other. So vectors include obviously the magnitude of the currents in this case, which is the digital data that gets transmitted across your network. But it also includes the actual phase angle or the angle of the current vector, which is basically time information. So it's quite critical that your teleprotection channel has deterministic latency so that the angles of the vectors at the local end match the remote end. And you can see there that both of those three-phase vector diagrams are in sync, okay? So the way the scheme works at the remote end, the protection relay compares the remote end current vectors with the local end, does a vector sum addition, and if the vectors sum to 0, that means that current flowing in the line at one end and out of the line at the other end are in sync, so there's no spill current or no fault on the transmission line, and hence no fault, so it's all good. But what happens if we get some sort of a communications issue that could cause some delay variance in our communications? That results in or can result in a rotation of the current vectors at the receiving end, the remote end. And once again, the remote end relay will try and sum the current vectors. This time though, there's an angular difference from that rotation caused from the communications issue. That will mean you'll get some current or spill current being detected, some difference in the two current vectors, which could trick the relay into thinking that there's a fault on the line and could cause the relay to pick up and trip the line, which is not good, obviously. So we've tripped for a problem with our communications network, which we obviously want to try and prevent. So anyway, we'll give you some, as we work through the presentation today, we'll unpack that a bit more, and that's one of the main focuses of our presentation today. So just a summary on line current differential. It sends both current vector magnitude information and time information, the current vector angle information via the teleprotection channel. It is sensitive to changes in channel delay from jitter and swapping to alternate paths with different latency, so that's certainly key considerations for teleprotection. The protection relays can use ping pong method for calculation of latency. Some of you or most of you were probably at the presentation yesterday on time sync, so we'll cover off some of the topics from yesterday's presentation as well today. And in practice, look, the guidance I try and stick with is we should make sure that total jitter and path asymmetry should not exceed 0.25 of a millisecond, which equals about 5 degrees of vector angle rotation in the system. That's just guidance. Like obviously if you're using precision time protocol or PTP, you can far exceed that, but certainly if you're using the ping pong method, 0.25 milliseconds is what I've found is the maximum you should permit with your latency and jitter. Just a bit about time sync. So, as we said, the protection relays themselves can use a ping pong method where they send a signal through the communications network, and they look for that return message coming back to the relay. Then they calculate a round trip latency and determine the actual latency in one direction by simply halving the return trip time. So that's why one of the reasons why symmetrical latency is so important, because the protection relays actually use the round trip time, halving the round trip time as their means of calculating the single path unidirectional latency. We can also use local time sync to the protection relays at each end. Typically this could be via GPS through a clock at the substation using a 1 pulse per second input on the relay, or it could be using precision time protocol as well. Or alternatively, you could use some sort of a distributed time sync from the communications network itself using SyncE or some other means across the network. And considerations of which options to choose include the reliability, redundancy and failure modes of the time synchronisation system, the communication system and the protection system. But typically I'd say that, look, if a protection relay offers a local time sync method, you should probably use that over and above using ping pong method. I'll hand over to Brenton now to take you through TDM.
Thanks, James. So C3794 gets a special mention at this tutorial because due to its widespread use, and it's basically the latest in a line of protocols used for teleprotection, superseding co-directional G703 and others before it. Shown here are the pair that make up a C3794 connection. They're protection relays on the left and the MUX cards on the right. The protocol, as it says up there, defines a number of 64 kilobit per second optical interfaces up to a maximum of 12. In our experience, N as the number of channels here is most nominally set to 1. The good thing, one of the positives of C3794 is that it's supported via an RFC for conversion to packet, and some of the eagle-eyed amongst you may notice the missing dust caps that have been reinstalled. So some of the important characteristics of C3794 for later in this discussion include the synchronisation of the protection equipment transmit interface is synchronised to the receive from the multiplexer equipment, so the timing is provided by the multiplexer equipment. There are limitations set for local jitter, as James mentioned, and the protocol also uses one's complement for error rejection. So you can see on the slide here that for each data bit there's 2 positions to be filled, and that's 1 and its complement for encoding on the wire. Again, as touched on by James, the ping pong timing method can be used by protection equipment, and it uses half of that round trip delay to offset the comparison of current vectors. Unless, and as he said, unless interlocked or qualified with additional fault indicators, that can result in the maloperation of, asymmetry in the telecommunications channel can result in maloperation of the protection scheme. Above and beyond what's in the standard, some of the things or additional requirements may include availability and reliability. It can be NEM derived or equivalent for your location. The end-to-end latency is not specified in the standard, so you need to be conscious of not only your cycle times, but also manufacturer specifications, and also asymmetry is not defined. So as we mentioned earlier, you need to consider how much asymmetry your schemes can tolerate. So C3794 is fundamentally a TDM protocol, or time division multiplexing. TDM is a method of sending multiple discrete signals over a single transmission medium, and each signal gets a fraction of the transmission medium's time to transmit its data. In this way, the higher speed channel in the middle here services the lower speed interfaces. This means the 2 ends of the communications channel must be synchronized to ensure that traffic in goes out the right connection. Importantly, the data sources don't necessarily need to segment the data, but they can do, as shown up here. For example, Ethernet cards for over TDM perform that segmentation. TDM has some common known titles, PDH, SDH and SONET. This diagram shows the components that contribute to the end-to-end latency of a TDM connected circuit, and each component adds a nominal amount of delay, and if configured correctly, the return path has the same delay. However, it is possible to have incorrect configuration and create a mismatch or asymmetry in your path by provisioning circuits one way over one set of equipment and having the return path over separate equipment, or a different channel path. As we said, time synchronization is required for TDM, and there's 2 main ways of setting up this synchronization. You can either have an ordered list or use SSM synchronization status messages that advertise quality of clocks, and the equipment makes the decision itself. We now briefly discuss C3794 support on packet networks and how we can emulate it. So, contrary to some beliefs, packet networks were not invented by Keanu Reeves in 1999. Packet networks are a mature technology with many challenges solved over time. Packet networks are non-deterministic, but yes, the use of dynamic routing protocols for forwarding paths means that they may change as the network changes. And there is no inherent need for time synchronization. So this needs to be considered when we look at emulating a TDM or synchronous channel like is used for C3794. Up here are some of the traditional components that are used to create a packet switch network. However, modern packet switch networks blur the lines between these building blocks. It's also important to note that more and more substation services are becoming accessible only via a packet switch network connection. There are also almost unlimited topologies that you can create with the basic network building blocks for a packet switch network. So MPLS, or multi-protocol label switching, IP and TP, they're effectively the same thing at the data plane level. However, they are very different from a control plane perspective. I'll summarise TP and IP as MPLS TP having a centralised intelligence for the control plane versus the distributed intelligence of the control plane for IP. The pros and cons are both there are pros and cons to both, and with anything, advocates for one over the other generally have strong held beliefs to why which one is superior. And as with any good problem, it's not generally a case of which is right or better, but what is a question of what is the problem you are trying to solve. That being said, both can become complicated very quickly, and I've found myself at the bottom of many a rabbit hole discussing MPLS networks technologies. Why do we need packet networks? They're good at a lot of things that are on the right-hand side of this slide. This slide attempts to illustrate both the bandwidth utilisation and traffic resilience of some typical substation services. So as I said before, RFC 5086 describes a method for encapsulating structured TDM signals as pseudowires over packet switch networks. The diagram that we have on the screen here shows an IED on the left-hand side, playing out bits via C3794 into a packetization device that's waiting to collect a number of bits of n by 8-bit multiples for packetizing them and sending them out on the wire. In the middle of the diagram here, we've got in-flight data that's been packetized. And on the right-hand side, we've got a playout buffer that stores several of those packetized frames before beginning the playout, so that any delay variation across the MPLS network can be compensated by floating that playout buffer depending on when packets arrive, to compensate for the packet delay variation that we have in packet-based networks. So, as I mentioned a little bit earlier, there are sources of latency in this system. Some of the fixed latency components include the packetization latency. So if I'm waiting to packetize 8 bits of data, that's going to take me about a millisecond. At the far end, the playout buffer, I'm going to wait for a certain amount of frames that I decide will compensate adequately for the packet delay variation on the network. And so that can be in the order of however many milliseconds you like. But once you've selected that, it should be a nominal delay that is added to your overall delay. The variability comes in the middle with the MPLS routers, the packet routers and the packet network, where simple things like waiting for the next largest packet to be played out can affect the latency of each individual packetized unit. So, as we said, C3794 is a TDM protocol and therefore requires a clock source. As shown here, we've got two methods of providing that clock source. The two of them are, the top shows service conversion equipment, or the C3794 conversion equipment time solution, where one acts as master and the remote end syncs off of it. And again, the protection equipment syncs off of the converters. And in the lower half, we have a network time solution. So if you didn't go to yesterday's D2 tutorial on time sync, the 884 technical brochure can catch you up on how you might provide some of those titles named up there, SYNC-E, 1588, P2P, and others. So to perform circuit emulation, some settings need to be symmetric at the end stations, and some need to be consistent on all the participating nodes. We haven't mentioned QoS yet, but in order to minimise the packet delay variation on the network, having quality of service to prioritise the teleprotection over almost everything else, with the exception of network control, because if you can't control your network, you don't have one. Making sure that the teleprotection packets are serviced first ensures that you have the most stable transfer times. Once you've done everything, you end up with this. This is a C3794 frame on the wire, captured via Wireshark. Unfortunately, at the bottom, Wireshark thinks that our C3794 data is Ethernet, but we'll ignore that. What we've got here is a Ethernet frame for transfer over the wire. We've then got a service label to mark our traffic distinct of other services between the same two endpoints, and then a transport tunnel label, which provides that forwarding path. And that last bit there, as you can see, our pseudo wire sequence number allows, even if our packets arrive out of order, to make sure that they're ordered in the buffer and get played out consistently. So we'll now discuss proof of concept and in-service testing and run through a case study. So, as goes hand in hand with any task and perhaps part of a good engineering management system, it's always good to have a target state in mind. For the purpose of validation, it can also be beneficial to understand the design constraints and limits, and in this way, performing a failure modes and effects analysis can help inform the testing that you do. As James said earlier, that can also be an opportunity for the telco teams to discuss the concerns that the protection teams may have, and as a takeaway from the message from the keynote regarding engagement of stakeholders yesterday morning, if you work in separated telco teams, engage with the protection teams as early as possible to make sure that we don't end up with a breakdown of communication, let's say. I'll now hand over to James to run through our testing.
Thanks, Brenton. I'll be running through a bit of a case study from the engineering and commissioning of one of our teleprotection circuits in the Evo network. But first up, look, I'll just describe how we approach in-service teleprotection testing during commissioning. Okay, so obviously we're looking at a hugely complex system here. You've got protection relays talking to C37 to 94 to IP converters. Then you've got the MPLS network itself. So you've got to make sure you're testing each component and each system within the network. It's not good enough really just to test the and during your commissioning, run tests on the protection system itself. You've really got to understand what's happening on the actual communications backbone, and just understand the latency, jitter, etc., and whether you are, you're oversubscribing the network or causing any issues that are going to cause loss of the actual communications network, or introduce some sort of delay. So this diagram just shows the overall teleprotection testing setup. So we've got, firstly on the power system side, we've got a couple of protection relays with a Doble injection test set at both ends. Doble's one brand, you can use Omicron as well. It's just an protection injection test set. You've got a protection test laptop connected to the protection relays, and also the power system simulator, that injection test set. Then on the communication side, we've got some packet injection test sets, some Y1564 test sets connected into our two routers at substation 1 and 2, which allow us to inject simulation traffic for both teleprotection, but also importantly, we also want to inject background traffic. We'll run through the tests in a moment, but important to run some oversubscription tests on your network, just to make sure that if you get some sort of flooding event, oversubscription on your network, you're not going to affect the teleprotection. So the case study, this is the actual setup. It's a very complex setup, probably overly complex to be honest. So down the bottom there, we've got our transmission line, single line diagram. So it's a 3-terminal transmission line with a T connection at terminal station 2 there in the middle. Got protection equipment, obviously protection relays at each substation. At terminal station 1, the protection connects into a C37 to IP converter, and then into a MPLS router. You can also see there we've got our Y1564 tester connected into the router. Then go via a couple of intermediate substations. When we get to intermediate station 2, the MPLS network then hands off onto a TDM network. So we come out of our router into a C37 to IP converter, back into C3794, and then into a TDM, a PDH network multiplexer. Then we go across to terminal station 3 and then back to terminal station 2 via the PDH network. And that then supplies C3794 to the protection system. The reason why this is so complex, like obviously with protection, we try and have diverse paths for our X and Y protection. So this is the X protection setup that uses the diverse path, which goes the long way around the network, if you like. The Y protection uses, in this instance, direct fibre, dark fibre, actually on the transmission line itself. So we've tried to go the long way around to avoid any I guess common mode failures. If that fibre were to break, we don't want to take down both the X and Y protection. So we ran through a number of tests during commissioning. Like I said, the first test we run through is an oversubscription on the MPLS network. So we inject 2 gigabit traffic on the MPLS network. For this test, by the way, we have to disable all the alternate paths on the network, just so that you're forcing the oversubscription traffic through the actual path that is also used for the teleprotection. Given that we've got a 1 gigabit per second backbone, obviously 2 gigabits you're oversubscribing by a factor of 2. At the same time, we're also running via our injection test sets some current injections into the protection relays to simulate the line differential traffic. And we also ran obviously multiple tests just to make sure we were confident we were getting consistent results. So this is a summary of some of the testing we did for this test. So if you look at the latency figures, the top two are the C3794 converter latency as measured on the actual IP converters at each end. So getting very consistent results there, no real change between the different tests as we injected the oversubscription in the middle there. The relays also measure the channel lag. This is the round trip time. Once again, you can see there the X relay channel 1 lag didn't really change between tests. So, you know, before the test it was the same as after the test, right? The important thing to note here though is down the bottom there, during the actual injection, we saw no real observed difference in the teleprotection latency or jitter, okay? So we got a pretty consistent 314 microsecond latency during the first test and then 309 microsecond of latency during the second test, which is pretty minimal, and the jitter remained consistently around that 3 microsecond level throughout the entire test, and that's the normal background jitter figure we see on the network. So this just really indicates that all of our quality of service parameters are working correctly. All the teleprotection traffic is obviously high priority traffic. It's being prioritised correctly within the routers, and the traffic that's being dropped, if I go on to the next slide, this is a screenshot of the actual network test set. And what that's showing is that the simulated background data traffic is showing about a 50.8% frame loss. You know, for 43 megabits per second received on a simulated 900 megabit per second stream. There's also another 900 megabit stream, by the way, running in background that isn't actually on this test set, hence the oversubscription. And that's the first line there, line 1 on the actual test set itself. So that's that's the line, second line, the line 3. That's the background data traffic. So it's showing for that, like I say, that 900 megabit per second stream. We're getting 443 megabits received at the far end. Coming back to line 1, that's the simulated teleprotection traffic. We've got a, what is it, a 2.6 is it, megabit per second simulated teleprotection stream, and we're seeing 2.6 megabits received at the remote end with no real FDV, that's the jitter, 3 microseconds, and 100% availability on the teleprotection, which is what we want to see. The second test we ran was just the effect on protection relay power cycling. So we ran this test 4 times here. So once again, each test, with the exception of the one in the middle there, was successful. So with the first test, powered cycled the relay, all good. The relay then recalculates its round trip time when the comms comes back. That was all good, and it then uses that for the phase angle calculation in its protection algorithm. So slight difference there. There was 181 degrees before the test. It went to 178 degrees after the test, and you can see some slight differences there if you come to line 3 there on the relay channel 1 lag. The lag went up by about 90 microseconds, I think it is, which just indicates that it's using the ping pong method. So when the channel came back up, the relays did a ping pong time calculation, and there was some difference in the round trip time detected, and hence the latency was affected a little bit, but still within the parameters that we accept, which is that 250 microseconds that I spoke of earlier. Once again, the other tests, the last 2 tests were successful, but during that test in the middle, we did observe that the relays didn't actually recover when the communications came back, and required the C3794 converter to be rebooted in order for the protection relay to start working again. Don't know, we didn't really get to the bottom of why that occurred, and I must say this was during testing. We've never observed this actually in production. I guess the important thing is that it didn't actually cause any maloperation of the protection system other than the communications was down. And we know that if this was to occur in service, it's a matter of sending a protection technician to site just to restart the C3794 converter. This is once again part of the test 2 test results. So we've observed that on the C3794 converters, if the network's normal, you've got your protection relays powered up, they're providing that C3794 time synchronisation, being looped back into the converters, and then the system's normal, so the time distribution's working in a loop throughout the entire circuit. The system's very stable, those regions in the middle there where you've got a solid green and a solid blue line almost, just shows that the latency is deviating by about, I think it's about 60 microseconds or so, which is all good. But what happens, this is during that test on the previous slide, so what happens when we power cycle the protection relays, we actually break that loop back of the timing signal in the protection relays at each end. And when we break the loop back, the observation is that the C3794 converters go into a bit of a free-running time mode, searching for a synchronisation signal to be returned. So that's what those larger deviations are for the four sections of the graph there. But once the communications comes back again, once the protection relays are turned back on and you get that loop back, the protection relays, the actual system settles down again and becomes stable. But interestingly, it becomes stable at a different latency figure. So that's one reason why we saw a bit of a jump in the round trip time latencies and the ping pong method calculations during each part of this particular test. I would say that's an observation. It doesn't actually affect the operation of the protection system in any way, providing the relays are calculating the latency correctly. They will be compensating, obviously, for the phase angle of the current vectors. The third test we ran was the effect of the IP C3794 converter power cycling. So this was all successful. So what we have done though in our system, we're a little bit nervous about the communication system flapping. If we were going to have some sort of intermittent communications fault in the system, we don't want the communications coming up and down rapidly. So we've introduced a script in our in our system which fails the communications for a period on loss of communications. But this test, once again, worked perfectly, really. So there was really very little difference in the latency and observed vector phase angle during the test. It went from 181 degrees to 183 degrees, and a slight variation there on the latency figures. All good. So the last test we did was a disconnection of the MPLS backbone itself. And this is where that script really kicked in. So when we get a failure of the communications backbone, the network will hard fail for a period of 3 minutes, just to stop that flapping effect, so we don't get communications coming up for a few seconds or so, going down, etc., because we figure that might cause some problems for the protection relays themselves. But once again, very, very stable here. In fact, when the backbone goes down, we figure that the relays, they're still receiving the simulated C3794 signals from each end with the time, and that's how they're getting their clocking source for operation. So observation here, look, we think this is correct, that we're not seeing any difference in latency calculations or phase angle calculations between the pre-test and after the test. All those figures are identical, or very close. So we think that the relays aren't really recalculating their round trip times during this particular test. So testing conclusions, we ran 4 test scenarios to determine the effects or the failure modes and effects for both protection system and communication system failures. All the results, by the way, they're inclusive of the actual system errors, but also the test equipment measurement errors. All the test equipment was synchronised from GPS, so we'd expect that to be very minimal, but it's still got to be noted that, look, it does include obviously your testing errors as well. It's not just the actual system. We observed a maximum 4 degree error with the target allowable of 5 degrees, so we're within the actual target we set for ourselves. And the observed jitter and path asymmetry was always well within that 0.25 millisecond maximum threshold we'd set ourselves. So the following was monitored. As I said, we monitored the X-communication, X-relay channel lag, the X-relay phase angles via the injection test sets, the C3794 IP converter latency, the network Y1564 tester latency jitter, drop packets, etc. And the router statuses and alarms were also monitored. I'll just briefly talk about cybersecurity. So with an MPLS network, it's all about having a converged network. So you've got a number of different services running and sharing the same infrastructure, and they're all competing for priority. So this is an example from our system, the way we've architected the network. So got things like SCADA services, our operational systems running over the network, obviously. We've got our teleprotection services also on the network. And then we've got a bunch of corporate services also running over the network. So we recently embarked on like everyone I guess is embarking on a cybersecurity journey. So the first starting point for us was to map our our existing architectures onto a using the IC 62443 Purdue model. We mapped it, into a security architecture. So starting at the top, you've got your enterprise systems. Then we've got a like a DMZ, if you like, between the enterprise systems, the IT systems, and our OT systems below, with some firewalls, etc. there, and some other protection. And we've got our SCADA master station, our ADMS system networks back at the control centres. And then down the bottom, we've got our various outstations. So we've got substations with, we've divided the substations into three zones. There's a supervisory level zone that has all the SCADA equipment and interfaces to the protection relays. We've got a process level zone, which is all in 61850 speak, it's all the sampled values and goose messaging in the station between devices. Then we've got the physical infrastructure itself, the electrical network down the bottom in that level 0. So importantly, we consider teleprotection to be separate from our zone substation security zones. And that's for one very good reason, which I'll get to on the next slide. So the risk with teleprotection is that it offers a very low level, layer 2 point-to-point IP service between substations. So it's very important that we're not bridging our networks between substations. So just understanding where the demarcation points, the different security zones within your substation is very important. 62443 is an excellent way to approach this. It uses zones and conduits model to understand the different security zones, the boxes, the green and purple boxes here on this diagram, and also the conduits between the boxes, the connections, and understanding it just allows you to unpack it and understand the risks and controls you might want to apply to the zones themselves, but also the connections between the zones. So on this diagram, this is the substation security architecture. We've got our SCADA master station up the top there, the ADMS zone. It talks out via the MPLS network. We've implemented a hub and spoke configuration where all the substations are on a spoked network. They all point back to the SCADA master station as the hub, and that really enables us to bring the firewall back to the hub of the network, so we don't have to deploy firewalls at each substation. Substations are actually protected centrally back at that master station central site. Out in the substations itself, we've got a supervisory zone, level 2, which is the SCADA, all the SCADA protocols, the MP3, 61850 MMS protocol to exchange alarms and statuses, etc., between devices and also back to the SCADA master station. We've also got, we're starting to deploy cybersecurity sensors out in our zones, so they're intrusion detection systems that monitor all that traffic. Then we've also defined a process zone that's kind of aligned to IC 61850 process buses, if you like, that just contains all the goose traffic and 61850 sample value traffic on separate VLANs within the substation. Then we've got our teleprotection zone itself, completely separate, that has a connection then back through the MPLS network using a layer 2 pseudo wire connection back to the terminal substation at the other end. Importantly, that's all kept segregated from the other parts of the network. So a few conclusions on cybersecurity. Considering TDM and MPLS as transport mechanisms, they both transport multiple services, so they can be both considered to present similar security risks. Need to make sure we keep our traffic segregated within those networks. Network segmentation, that's always the best place to start, and applying 62443 zones and conduits is a good place to start. Just mapping your network into a Purdue model is a great way to visualise that. For OT systems, substation systems, we flipped the generalised IT security concepts of confidentiality, integrity and availability on its head. So for OT systems, availability is the most important aspect. We need to make sure systems are available. All of our protection systems and control systems are operating and 100% or close to 100% available as we can get. Also, integrity is important. We can't afford to have teleprotection, the integrity of the system being compromised, and probably confidentiality not so much. Still important, but typically we're running our systems on private networks via private optical fibre, OPGW and the like, so the opportunity for confidentiality compromise is pretty minimal, and the data really isn't, it's not like credit card data or something like that.